Hello and welcome to another episode by Mrs. Technically Speaking. And today I'm looking at organic chemistry with emphasis on isomers. So, all our isomers are structural isomers in the sense that they have the same molecular formula. What does molecular formula mean? It means it has the same number of carbon, hydrogen, and in other cases, it has the same number of carbon, hydrogen, and oxygen. But the structure of the formula differs, and that is the reason why it gives rise to three different kinds of isomers. So the first one is a chain isomer. A chain isomer also has the same molecular formula, same number of hydrogen, same number of carbons, but the chains are different. For example, butane and methylpropane. Butane has four carbons, and methylpropane also has four carbons because in methyl there's one carbon, and in propane there are three carbons, making that also four carbons. Same with the hydrogen, there are 10 hydrogens, and there are 10 hydrogens here as well. Right. So now we have to move on to positional isomers. Positional isomers also have the same molecular formula, so same number of hydrogen, carbons, and oxygen if there is, or halogens for that matter, but the position of the functional group is going to be different. Let's look at this example. Propan 1-ol and propan 2-ol. These numbers show us the position of this ol, which is an hydroxyl. This hydroxyl is a functional group. So propan 1-ol is saying that the hydroxyl group is on carbon number 1 of the three carbons. This 2 is saying that the OH, the hydroxyl group, is on carbon number 2 of the three carbons. So the position of that functional group hydroxyl is giving us a functional isomer because the images of the structures will be different. Functional isomers also have the same number of molecular formulas, but the functional group is going to be different because of the position of that functional group. Here they are saying butanoic acid, which is a carboxylic acid, and ethyl ethanoate, which is an ester. So the position of the functional group inside of these two compounds are different, and that is the reason why it is giving rise to a functional group. Because if you change the position of the functional group in this example, you are changing the homologous series as well. So butanoic acid has four carbons, and ethyl has two, and ethanoate has two, so that is also four carbons. And the number of hydrogens will also be the same. So now let's go on and look at more details of this topic. So the first one we want to refer to is the chain isomers. That means they have the same molecular formula, but their chain lengths are usually different because of a substituent group. The example they gave us was butane. So butane is but is 4. So it's 1, 2, 3, 4. And it's a saturated compound. That means it has 4 bonds around each carbon. So this is now your butane structure. It has 4 carbons, and if you count it, it has 10 hydrogens. Now, what is the isomer of this? The isomer of this can only be this structure, because if we count 1, 2, 3 or 1, 2, 3, we will still get the same IUPAC name. So again, here we can fill it up with our hydrogen because it's also saturated. So now we have 1, 2, 3, and this is a methyl group here. So this is 2-methyl, 1, 2, 3, propane. 1, 2, 3, 4, it still has 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 hydrogens. Same number of carbons, same number of hydrogens. Chain isomers, this is a shorter chain, a chain of 3 carbons and 1 substituent group. Here it is a chain of 4 carbons. They have the same molecular formula, C4H10, but their structures are different. And what is specifically different about their structure is the chain length. Right, the next one we have to speak about is the positional isomers, right? So the next one is our positional isomers, and that is going to be the position of the isomer itself. So let's take, for example, but 1-ene and number 2, but 2-ene. Number 3 is going to be the ones that they gave us, which was propan 1-ol and propan 2-ol. Just to add to this some more content, I also want to remind you that when the OH is on the first carbon, it is a primary carbon, and this one is on the second one, it is a secondary carbon. It would be tertiary if it had maybe methyl propan, so the presence of the methyl would then make it an advanced structure, tertiary. So butan 1-ol, let me also change the color for the drawings. It will be 4 carbons, 1, 2, 3, 4. 1, 2, 3, 4. 1 means that there's a double bond on carbon number 1. 1, 2, 3, 4. Doesn't matter which side you start counting. 1, 2. So it means that there's a double bond there. Then each carbon must have 4 bonds. So there we're filling it up. This one has 1, 2, 3. So it only needs 1 more. Here it needs 2 more. And here it needs 3. Right? So as much as the functional group has changed from carbon 1 to carbon 2, it hasn't had any effect on the homologous series itself, right? It is a positional change that has taken place. So but 1-ene and but 2-ene are positional isomers. What has changed? The position of the double bond, which is the functional group. Propan 1, 2, 3 on carbon number 1 is the OH. 1, 2, 3 on carbon number 2 is your OH. So again here, what has happened? The position of the hydroxyl group has changed from 1 to 2, and that is giving a rise to a positional isomer. So if you want to have a hack, we are saying that if these numbers change for the position of the functional group and it's still within the same homologous series, then we refer to it as a positional isomer. Right, let's move on now to the last one, which is our functional isomers. Now, functional isomers, what I want you to remember about them is if you change the position of the functional group, the homologous series changes as well. And we have 2 sets of that. The first set is aldehyde and ketone. And our second set is carboxylic acids and esters. So if the functional group changes between a carboxylic acid and an ester, it is functional isomer. Aldehyde and ketone, it is also functional isomer. So now let's look at the structures of these organic compounds, right? So when we talk about propanal, right? Propanal is an aldehyde. So it's 1, 2, 3, double bond O and H. Ketone, propanon, 1, 2, 3. It is here in the middle. So you can see that if you move the position of the functional group, 1, 2, 3, 1, 2, 3. If I move this functional group here from carbon 1 to carbon 2, it is going to look exactly like that. And if I move this functional group from carbon 2 to carbon 1, it is going to be an aldehyde. So an aldehyde has the formal group on carbon 1, right? So it must be on the first or last carbon. If it's on the last carbon, you start counting on the other side, so it's still carbon 1. Then the ketone has the carbonyl group right in the middle, always in the middle. And remember, the middle can also be, if you have four carbons, it can be on carbon 2 or 3. So it is never on carbon 1. Carboxylic acids and esters are exactly the same. If we have a carboxylic acid, we are saying that we still have, similar to this, we have it at the end because the H must complete that molecule. This is a carboxylic acid. But if it's an ester, it is in the middle of carbons. It is in the middle of carbons, right? But it's the same structure, in other words, because here is the structure here, functional part. And here's the very same thing. But what is different? This one is at the end or the beginning. Carbon 1 or carbon or the last carbon. This one is in the middle. If you shift it from the middle to the end, it's a carboxylic acid. If you shift it from the end to the middle, it is an ester. The same goes for this side.